It's a pleasure to have Yusuf Baris Kartal talking about Equivariant.
Thanks. Thanks for the opportunity. So, can everyone hear me? Okay. If I, go, there's silent, just warn me so I can raise my voice again. So, I'm going to talk about some constructions in topology and in category theory that allows us to define equivariant versions, those equivariant and homotopical versions, spectral versions of some well-known invariants in symplectic topology. So all of this is joined with Laurent Cote and partially with Cheuk. And the last two slides with Cheuk. Okay, so let me start by briefly introducing Morse theory. Okay. So Morse theory is the study of manifold topology using functions and the gradient. But functions can actually be complicated, so we restrict to a special class of functions called Morse functions. This is an example. And a Morse function is characterized by two properties. One of them is that it has isolated critical points, and the other one is near the critical points. The function in some coordinate system looks like this. Okay, so some constant plus minus x1 square plus minus x2 square plus minus that's xn square where n is the dimension here. Okay. So here's some picture. Okay, so this is the examples in R2. Those are the local examples. Okay, you have near a critical point. The function can look like one of these three options in R2: x square plus y square, x square minus y square, and so on. And the blue dots in the middle is the critical point, and the yellow lines show you the gradient flow of it. Okay, so for instance, this one is the source. This one will sink, etc. Okay, let me give a more global example. Okay, so consider the surface of revolution of the circle, and it's a torus. Okay, you put the torus on the table, and you consider the level function. Okay, you consider the height. So this is like a projection to the z-axis. Okay, and this is actually a Morse function. And the points that I marked by blue are the critical points, the 4 critical points of this function. And these yellowish, brownish lines are the gradient trajectories of it. Okay? So, what can you do with a Morse function? Okay, very classically, you can obtain handlebar decompositions. Okay? And a bit less classically, but it's not less classically, still classically, you can actually obtain a complex computing homology. Okay, a complex generated by critical points, a 4-dimensional complex that computes the homology. Okay. Let me elaborate a bit. Okay, so to compute homology or cohomology, doesn't matter. You need the data of the critical points and the gradient trajectories between them. So gradient trajectories form a space, but the space doesn't necessarily have to be compact, but you can actually compactify. Here's a picture on how you compactify. Okay, so again, like this can be thought as a real example, or we can think of this as a schematic example. If you want, you can put a Morse function on the square, where the critical points are these corner points, and the gradient trajectories are the lines that I showed with arrows. Okay, so as you can see here, the gradient trajectories from y to x there's one here, one here, one here, but like they are parameterized by an open interval. It's not compact, but if you actually include broken trajectories, meaning the concatenation of the trajectory from y to w and w to x, and similarly y to z and z to x, then you are getting an interval, so it becomes something compact. Okay, so here the broken gradient trajectories from y to x are parameterized, broken trajectories are parameterized by the closed loop. Okay. So can you actually, the question can you ask is, can you get more information about the homotopy from the Morse theory? And Cohen-Jones-Segal answered this as yes. This has been motivated by something else, which I will talk about shortly. But Anyway, how do you get this? So let's say you have a Morse function and you have some auxiliary data. I'm not going to tell what auxiliary data is in general, but for the Morse function case, it's just a metric, a generic metric. You can associate a non-unitary category, math called X. Okay, it's non-unitary. It doesn't have units. It's directed. And the objects of this category is given by the critical points of it. There are finite many of them, as if it's Morse. And so the homes from X to Y is the space of broken gradient trajectories of F from X to Y. Okay. And the composition is kind of silly, it's just concatenation. Any questions so far? I mean, in this example, for instance, okay, this is it's drawn in a different way, but there are 4 objects, and morphisms from Y to X are these arrows here, and the ones that are for composition are given by this broken trajectories. Okay.
Why make it united by adding just like the end trajectory?
Sure, you can do this.
Oh, but you don't basically.
I'm not using the units anywhere, but you can do this. Okay. There's something funny about this, its trajectories are like, those are gradient trajectories modulo R action, right? You're quotient by the translation. So somehow if you actually add the constant trajectory there, and if you quotient by the R action, you get something of negative virtual dimension. But, we can also artificially just add, I mean, its geometric meaning is somehow weird, but we can also just artificially add a unit. Yeah. Anyway. Okay, so for a generic, okay, so let me just make a small point here. For a generic choice of metric, the auxiliary data, this thing is a smooth manifold with corners. Okay, it's a smooth compact manifold with corners, broken trajectories. And so, you can use contrasting tone collapse because it's framed, right? So as it is framed, using this framing, it can embed it into some larger Rn, and using the trivialization of the normal bundle, you can write a map from a sphere to another. And what Cohen-Jones-Segal do is they actually apply the contrasting tone collapse consistently to all of these moduli spaces. To obtain essentially a complex, I'm not make this more precise, complex in spectra, like a chain complex in spectra. Okay. And then they take homotopy fibers in an iterative way to obtain a spectrum. So for instance, if you only have objects X and Y, then the homotopy fiber or homotopy cofiber up to some shift of this map from Sn plus T to Sn would give you what I denote by this absolute value at Mn. Okay, it's called geometric realization. I didn't write it here, but I'm going to use the same term again. Any questions?
Yeah, these are manifolds with corners. I don't want to have a common for manifold, which I know how.
So you actually, yes, for instance, let's ignore corners and just consider manifolds with boundaries. Okay, so if there is no boundary, of course you get a map from Sn plus D to Sn. If you will have boundary, you are actually embedding into positive real numbers like 0 infinity cross some Rn, and what you get is essentially a map from a cone. Let me practice this. So, for manifolds that boundaries, you get maps like this. Okay, and then the moduli space for this point and this point are going to be a manifold boundary. So when you apply the contract control that, you are embedding into 0 infinity cross some large Rn. And what you get is when you apply the contract control that, it's a map from the cone of this Yeah, I may be messing things up. There is some shift, etc. So this, and this is basically a non-homotopy of this composition.
Oh,
Okay, so I'm being a little slow. So I mean the higher dimensional moduli spaces give you the higher covariance relationship. Okay. Oops. So we're gonna do the same thing equivariantly, okay? But then there's a problem. Morse theory is not compatible with the Lie group actions. Okay, why not? So usually there are no equivariant Morse functions. And the example is if you have a free action of the connected non-trivial group on a manifold N, then the critical points of a Morse function are discrete, so they have to be fixed by G, but a free action doesn't have any fixed points, so you don't have any equivariant Morse functions. Okay, and solution to this is you extend the setup to Morse-Bott functions. I'm going to introduce this. I should have written this in M, maybe, but so there are plenty of equivariant Morse-Bott functions. And the example here is the same example. The non-example above turns into an example. You take a free action and you choose a Morse function on the quotient. Then the composition from N to N mod G to R is Morse-Bott. So, okay, let me say a little more about Morse-Bott functions. This is a generalization of Morse functions, and it's characterized by two properties. So first one is the critical set is not just a bunch of points, not discrete points, but it's a disjoint union of submanifolds. Okay, and the second property is near the critical points. The function has a very similar spatial form in some local coordinates, but except now you are actually allowing the number of variables to be less than the dimension. So the function can actually be constant, for instance. Okay. And the example is, again, you consider the torus, but now you put it flat on the table. Okay, and you consider the height function. There's a rotation action. Rotation action is free. As we argued, there's no Morse function that's equivariant with respect to the rotation. But the height function is actually Morse-Bott, and the critical points are given by these two blue circles. And these yellowish brownish lines are now the gradient trajectories. Question? Well, let me say a little bit about the main construction. So we pack the data of critical points and trajectories between them into something that we call a frame Morse-Bott logic category, okay, adjectives, etc. So in other words, we pack it into a category satisfying such that the set of objects is a smooth compact manifold. In the Morse example, it's gonna be the union of critical manifolds. Okay, so it may have components of varying dimension in particular. And if you have two components, x, y, of the objects, then I'm going to write the set of morphisms from a point of x to a point of y by mxy. And this thing is a manifold with corners. And then you have domain and codomain maps. Of course, this is part of the category structure. And you have composition, but since composition is defined on the fiber product, because the target of one morphism has to be the same as the domain of the other morphism. And then I have this prefix frame there. So framing normally means a trivialization of the stable normal bundle. You embed into some Rn, and then a stable framing at least. Then you trivialize the normal bundle. In our case, it's a relative framing for twisted relative framing for this projection map, for the evaluation map from mxy to x. Okay, so this is the domain map. In other words, we have bundles, virtual vector bundles over X and over Y. And we have the following identities. This is part of the data. So you pull back the bundle. I didn't write pullbacks, but you pull back the bundle of X and the tangent bundle of X to MXY. And Bx plus Tx is the same as the tangent bundle of M, and ignore the R factor there plus Vy. Okay, so the reason I call this relative is because essentially this is trivializing Tm minus Tx, the relative tangent bundle of this map. And the reason I'm calling this twisted is because there are these other bundles in X and Y that's involved. It's a bit of a technical condition, but it's crucial. But I'm not going to touch this again. It's crucial for the work, but I'm not going to say much about this again. Any questions? Yeah. Okay. So the example is, of course, as you can guess, if you have a Morse-Bott function and you have to choose some data, but then you can consider the category with objects given by the critical manifolds, the union of critical manifolds, and the morphism bundles are again broken trajectories. But you can concatenate two morphisms only if their endpoints are the same. So and so we actually construct a spectrum out of a frame Morse-Bott flow category, and we call this geometric realization. It's a generalization of what Cohen-Jones-Segal is doing. It's again like some sort of application of relative application of controlling topology X. And so this is a sanity check. The geometric realization is actually equivalent to the underlying manifold. Okay, this is just telling us that we are doing the right thing. Equivalent meaning homology equivalent. And underlying manifold means, of course, you add a base point and take suspension spectrum, but you can ignore the parenthetical here, which just doesn't matter at this point. Okay. Okay. And if you have a G manifold, okay, G is compact, G is a compact Lie group here, okay, and you can consider an equivariant Morse-Bott function on EG cross N. This is for technical reasons, and I'm going to say how to drop this later. It's work in progress, but you can consider a Morse-Bott function on EG cross N. So, for example, you need a manifold model for EG. So when G equals circle, for instance, we can consider this infinite dimensional sphere cross N. Okay, and corresponding frame Morse-Bott flow category and its realization are actually G equivariant. And one result is that the realization is actually equivalent to N. But let me give you a technical warning here. The equivalence doesn't respect geometric fixed points. Meaning, both sides are genuine equivariant spectra, but somehow the genuine equivariant structure on the geometric realization side is not the right one. But you can do everything else. You can calculate homotopy fixed points, you can get, homotopy orbits, etc. Questions? I hope I have. Anyway, okay, let me just. Okay, this is all with Morse theory for now. Let me just talk a little about homology. Okay, so homology is Daniel introduced it this afternoon. It's an umbrella term for invariants defined using Morse theory on infinite dimensions. And so I'm just motivating you a little bit. So Floer defined this hugely successful invariance in symplectic topology as Daniel mentioned, gave rise to a solution to a major conjecture of Arnold, and half of mirror symmetry at least. And it actually has genuine applications in enumerative geometry. There is a major result of MacLean relating quantum homology rings, and proof goes through Floer homology. Quantum homology rings of bilational Calabi pairs, and the proof goes through enumerative geometry. And it will make symplectic topology with many other fields, including string topology, non-commutative geometry, and so on. So it's more for motivation. And so, okay, again, as Dai mentioned, there's an action functional on an infinite dimensional space, and Floer homology is the Morse homology on this thing. Okay, so Floer theory is Morse theory on infinite dimensions. So the data of critical points and gradient trajectories is actually all you need to define Floer theory. Sorry. Okay, my stopwatch will start. How long? When did I start?
At 2 minutes past 4.
Okay. Oh, yeah, I remember that.
Thanks.
So, okay. So let me just fix the setup. You pick a nice open symplectic manifold. It's all labeled manifolds, which Dai has spoken about. And the example that you can take is, you can just consider this example S3 cross R3. It's good enough for purposes here. And you consider the free loop space, in other words, the mapping space from S1 to M. And very classically, the Morse homology on LM is called symplectic homology, and it's denoted by SHMZ. So the example is you can think of this as a homology theory on symplectic manifolds. The example is, if you consider the cylinder, if you take its symplectic cohomology, you get this ring. So, okay, this is just a small remark here, a side remark, but this guy is, it may look very alien for a second, but it's actually a generalization of quantum cohomology to non-compact manifolds. It's not as weird if you are familiar with invariant geometry a bit more. And a small warning to avoid any confusion: the Morse function on the free loop space actually depends on the symplectic geometry of M. Okay, so symplectic homology is actually a symplectic invariant. It depends more than just the topology of the loop space or topology of M. So I promised to tell about Cohen-Jones-Segal's main motivation. So their motivation, of course, was to lift the Floer homology to spectra. What I mean by this is, if you have a space, you can take homology. If you have Floer homology, the question you can ask: is there a space or a spectrum whose homology gives you Floer homology? And the outcome is, of course, they didn't work out lots of details, but the outcome or expected outcome was more powerful invariants. For instance, you could take symplectic K theory instead of symplectic cohomology. And this field of Laurent theory was dormant for a while, but there's a recent resurgence. Recently, Abuzait Lambert, did some work on this, and they gave applications to dynamics. And again, in large, define the formula a spectrum, SHMS, which is a symplectic invariant. So you should think of this as passing to a final coefficient field. S is the sphere spectrum here. So instead of symplectic cohomology with coefficients over Z, you are taking symplectic cohomology with coefficients over S. Okay. And so, okay. Again, I mentioned talked about this, but this group here, SHMZ, is highly structured. It's a frame into algebra. And so the spectrum, ignore the space in quotation marks, the spectrum SHMS is actually expected to be even more structured. It's not a space, it's a spectrum. So it's expected to be even more structured. And the crucial part of the expected structure is a circle action. And more generally, I would say more about this maybe, but a frequent expectation is that Floer invariants carry actions with compact loops. So you can observe that free loop space carries a circle action, and you can actually induce an action with Morse theory using the previous construction. Okay. I'm being very sloppy here, it's a lot of but it's good enough for now. So let me just state this formula as a theorem at least. This thing can be endowed with a circle action, and the second one is a spectral equivariant version of Viterbo isomorphism, which Dahi mentioned. If you take the potential bundle, then this guy is circle equivariant equivalent to the free loop space. Okay, if you will be a little more precise, you know, it's actually a tone spectrum over free loop space, but you don't need to know this. Similar to, you know, string topology for free loop space, string topology at the spectral level being defined for the tone spectrum of minus TQ over the free loop space. Anyway. So again, some more advertisement. I think we can skip this. So, okay, let me just very briefly tell about an application. Okay, so the symplectic homology is not actually sensitive to topology of M. So, for instance, it can vanish even if M is very complicated. Okay, but there are actually ways of recovering rational deformation from equivariant symplectic homology, but the torsion part is lost. So, what we prove is you can recover integral homology, Morse-Bott K theories, complex K theory, and so on. From the equivariant homology of, okay, just ignore this space thing, from the equivariant homology of this spectrum. Okay. So, you know, again, like, surprising part is symplectic homology is losing all the information about the topology of M, and this connects, I mean, symplectic topology a little more with homotopy theory. This is more like clickbait, so I can skip this. And there are also expected connections to mirror symmetry. Right. And so, okay, during the construction, okay, we actually replaced M by EG cross, and this actually means loss of a lot of information. And so, for instance, the example is you can, you know, only obtain the completion of equivariant K theory from this. Okay, you know, depends on what you mean by equivariant K theory, of course, but you know, there is a distinction between genuine equivariant spectra versus Borel equivariant. Genuine equivariant carries more data, and we are losing when we product EG. So we wanna get rid of this EG component, but there is a problem. The Morse-Bott function can be chosen equivariantly, but the auxiliary data that I never told what it is. In the case of N, is just a metric for symplectic manifolds, just ignore it for the moment. You cannot choose the auxiliary data so that this guy is a manifold. Okay. But it still carries the structure of a derived manifold. The derived manifold seems sounds like a very scary thing, but it's very simple for our purposes. So you can actually extend the previous construction to this setting. But I mean by derived manifold is just the zero. It's just a zero set of a bundle of a section of a vector bundle. And so, you know, work in progress is to extend to this derived manifold setting, and the more, you know, and the Morse-Bott constructions to this derived manifold setting. And we are also working on weakening this framing condition and allowing these guys to be derived orbitals instead. But, yeah. And time for this. So let me just very briefly tell the motivation for the previous slide and some other stuff. So there are some physics-inspired conjectures. If you have a Hamiltonian G manifold, then an expectation is the action of Coulomb branch algebras in K theory and elliptic homology to act on the equivariant and symplectic quantum, so equivariant symplectic and quantum homology. So, and you expect some compatibility of the action. So we are working on verifying this. But I think I'm not going to give more details. I mean, I'm done. Thanks.
Thanks very much.
I don't know the construction of SHM with coefficients in the C spectrum, but I was wondering whether there is a canonical map from M, or rather a conventional spectrum to that map, and how connected is this map?
The canonical map from M to SHM,
Yes, is there one?
there is one, and you are asking how connected this map is.
Yeah.
Meaning the homotopy groups of the form. So I don't think it has anything connected. So yes, there is actually. There is. So you can see M as okay, so as geometric realization of some block category associated with Morse-Bott. I'm not ignoring everything Morse-Bott and Equivariant, and you can see I'm ignoring this. Okay, if you want, this is like this thing, and you can see that there is a geometric realization. Something else again. Let me just put some subscripts. Doesn't mean anything here. And to write a map from a geometric realization to another geometric realization, there is the notion. You use the notion of flow bimodal. Abuzai is using it a lot. And there's a flow bimodal. There's an MF and a G bimodal. And the bimodal is given by you use Morse trajectories, half Morse trajectories. Those are like spikes. And this is like a copy of C, if you want. Okay, so this is like the objects of this guy are Miltonian orbits. So this is an orbit, and this is a critical point of it. Okay. And as for connectivity, the cone of this essentially sees all these non-constant orbits. And the non-constant orbits can lie in various different degrees. There's very different things. Depends on who the sees, you know, it may be arbitrary, negative, arbitrary, positive. There is no general model.
And how did you recover the generalized homology groups from this? I mean, you said that a lot of generalized homology groups of M can be recovered from that.
Yes, so there is an action configuration. There's an action configuration on the side. But even if you remember the action configuration up to some peak equivalence, similar to like remember if the action has degrees in configuration, but if you for instance have a degrees in configuration on a vector space, it's like remembering topology. I'm allowing the change in the configuration in a very trivial way. And so okay, the construction if you have that's a very complex orient. Let's say if you have a complex orient homology there, like more of a case, let's just say more of a case complex case. But what you do is you take the homology of this FPSH, the level here, okay, and you apply homotopy orbits. And this is, of course, this is giving but you are taking the form to the contravariant. So you take a limits in inverse. And we call this an term. I'm skipping a step. Before you take inverse of it, this is a module over R star bracket bracket U. Okay. And for a general complex oriented theory, you are actually inverting all K theories. But for more of a K theory, it's enough to invert just U here, and then take a limit. And then this is killing all the non-constant orbits. And it's remembering the essential part.
All right. Oh, yeah. Just to be clear, so the spectrum shot of the other second point. The spectrum.
So SHM, maybe SHMX.
Yeah.
So there is an expectation for it to be photonic.
Okay.
So Reschkow recently started constructing a genuine photonic structure, but without short action. He constructed some identification of, like he constructs some, not a key because he actually constructed true action, something like that. But yes, so the expectation for is that this guy is photonic. you can actually get the for this being loop space, and it's also expected to be topological box homology of some category of the space. That's what we need that.
Right. Is there any other questions? Thank you.